Hi everyone, Mr. Chaffee here for our second Keystone Review lesson. Today we're going to be looking at different properties and laws of exponents and how we can use them to simplify and evaluate some different expressions. To get started, we're going to go over a couple of vocab words as a refresher. So we've got our exponent, which is the power that a number is being raised to, and the base, the number that is being raised to a power. And if I write out a little example off to the side, 2 to the third power, we've got our base of 2 and our exponent, our power of 3. So it's nice and simple, base and exponent. Now we need a couple of rules that we are going to have to use in order to solve a lot of the problems we're going to look at today. So off to the side here, I'm going to write out the rules that we will be taking into consideration for our exponents. First up, when we have like bases being multiplied together with different powers, we simply add the powers together. So for example, if I have x raised to the a power times x raised to the b power, or x is our base, we have the same base, but we have different exponents that x is being raised to. When we multiply these two like bases together, our final answer will have one base that has a power or an exponent of the sum of the two original exponents there. So that's our first rule. Second, when we're dividing like bases to different powers, like such, x to the a divided by x to the b power, we simply subtract the two bases, or the two exponents from one another. So our answer here would become x to the a minus b. And I should make it clear, all of these variables, they just represent numbers. X, a, and b, they're all just in place of a number. So this works for any real numbers that we're plugging in here. Now let's do one last rule here where we have an exponent being raised to another exponent. We're going to multiply those two together, which will look like this. If we have x to the a raised to the b power, that's really saying we have x to the a times b power. There you have it. Those are our three rules that we're going to need to use for the rest of our exponent review today. But now let's take a look at how we can apply these rules to a couple of different examples. First up, we've got our simplification problems where we're trying to reduce these down to only positive exponents. So getting started with the letter A here, we have 4 squared times 4 squared. We have our like bases of 4 here, and they're both being raised to the second power. So using our first rule, we could say that 4 squared times 4 squared is equal to 4 to the 2 plus 2 power, where we're simply adding our two exponents here, which is going to get us 4 to the 4th power. And another way we can look at this to prove this, make it a little more intuitive, we could also just write out what this means in terms of repeated multiplication. What I mean by that is if we have 4 squared times 4 squared, well, this first 4 squared says we have 4 times 4, which is being multiplied by our second 4 squared, which is another 4 times 4. Altogether, we get these 4 4s, which is the same thing as 4 to the 4th power. All right, let's try out the next one with our 2's here. Now we have 3 like bases, and it's going to be the same idea. Since we have like bases with every single one of these terms, we can still apply our first rule here. So we have 2 to the 1st power here. That's usually we don't write 1 when it's our exponent because that results in the number itself. Anything to the 1st power is itself. times 2 squared times 2 squared is going to equal 2 to the 1 plus 2 plus 2 power here, which in total is going to get us 2 to the 5th. All right, these next couple are getting a little bit trickier. Now we've got some variables and some constants in here. The easiest way to approach these is just to multiply by our constant terms first. So we can take our 2 times our 5 here, which is going to equal 10. Now let's consider our n's. So we have 10 n to the 4th times n to the 4th. All I did here was flip the order of this multiplication around because multiplication is commutative, so we can do that. So I brought that 5 out to the front to multiply by our 2, giving us the 10 there. And now we have n to the 4th times n to the 4th in the back, which we can use our first power rule again to get us 10 n to the 4 plus 4 power, or 10 n to the 8th power. Letter D is going to be a similar approach here, where it's going to be easiest to just multiply our constants together. So 6 times 2, that'll get us 12. And now we have our like bases, our x to the 1st and our x to the 3rd, which results in, well, I'll write that out again, times x to the 1st times x to the 3rd, which is going to give us 12x to the 1 plus 3 power, giving us a final answer of 12x to the 4th. All right, that was a look at our product rule. We've got our like bases with different powers, so we can add them together. Now let's try our second rule, number 2 here, which is our quotient rule. We're going to have to use subtraction this time instead when we're comparing our bases. So I'm going to recopy down letter A down here. We have 5 to the 4th over just 5 to the 1st. We have those like bases again, and this time, since we're doing division, we're just going to subtract our powers, or our exponents. So this is going to give us 5 to the 4 minus 1 power, which is equal to 5 to the 3rd power. And I'll write this one out so we can see what this looks like in number form as well. So we could say 5 to the 4th over 5 is equal to 625 divided by 5, which again, now we just have a regular division problem. And 625 divided by 5 is equal to 125, which is going to leave us with, or which is equivalent to 5 to the 3rd. We could do this even one more way. We can look at this a little bit differently here, where we've got 5 to the 4th over 5 is equal to 5 times 5 times 5 times 5 all over 5, which, when we have these 4 5s up top and we're dividing one of them out, we can cancel out one of those 5s and we'll be left with just 5 times 5 times 5, which is equal to 5 to the 3rd. So just a few different ways to look at that same problem there. They're all equivalent forms in solving it, but our final answer that we want to get every time is our 5 to the 3rd. All right, now let's try out B together. Now we have these constant terms out front, which are not the same, so those are unlike bases, which we will have to ignore for the time being. Let's consider our r's, which we have both on the top and on the bottom here. So now we're going to get 3 over 2. We'll leave that as a fraction. And we're going to keep our base of r and take our exponents and subtract using our quotient rule here. So we have 3 halves r to the 3 minus 1 power, which is going to give us 3/2 r squared. All right, 2 more of these quotient rule problems here. Let's try letter C together. So again, we've got our unlike constant terms here, which we're going to have to ignore for now in our simplification. And we'll get 3/10 times our base, which now our base is, we've got a 1 on top there, so we have 1 minus 3. So our base is being raised to the 1 minus 3 power, which is going to give us 3/10 b to the negative 2 power. And it says right here we should only contain positive exponents. So when we have an exponent that is negative, that means we are taking the reciprocal of that base. So instead of saying this is b to the negative 2, we can simply rewrite this as 3/10 b squared, where we're taking the reciprocal, so this b squared term ends up in our denominator. We end up dividing by that, and our power can now be represented as a positive value down in our denominator. Let's try out one more of these together. We're going to see that same concept pop back up in D, where now we have 14/6, or 14/6, which again are unlike bases, but we could also say we can factor out a factor of 2 here, so I'm going to go ahead and do that as well, just because we can. So if I divide out 2 from both of these terms, we'll be left with 7/3. And I'm going to write my like bases. I'll do those up on the top again, where we get x to the 4 minus 5 power. So again, just subtracting the exponents of our like bases are 4 and 5. And that's being multiplied by y to the 7 minus 4th power. Which, once we simplify that, forgot my equal sign, we will get 7x to the negative 1, y to the positive 3, all over 3. And again, notice we've got that negative 1 here, and we want to have a positive exponent, which means we're going to have to take the reciprocal of this term. That's going to get us 7y to the 3rd, and our x term goes to the bottom, so we have 3x to the 1st, which you don't need that first power there, but I like to write it anyway, just so we can see it.